Cool. So hello everybody. My name is Lukas. I work here at Sentry. Specifically, I work at the Sentry JavaScript SDK team, so with Secret, what she presented before. So if you install one of these nice @Sentry browser packages with npm or the package manager of your choice, then that's basically what I and my colleagues are working on. Some fun facts about me. I am an aviation nerd. I'm probably spending way too much time in Flight Simulator. A couple of, 1.5 years ago or so, I started getting into archery, which for me is really a fun sport where I also get outside, which is nice. And I'm also kind of interested and passionate about software testing, some advanced testing techniques, speeding up tests, making them stable. And today I thought, well, let's maybe talk about one of these testing topics, which is mutation testing. Or an alternative title would be how to test your tests. So before we get into it, maybe I can get a show of hands. Who of you has already heard of mutation testing before? Okay, that's a couple of people. That's nice. Maybe later on we can talk a little bit about your experiences, because I'm really interested about this. But yeah, today we'll talk about what mutation testing is all about, what it can do for you. Then we will take a look at mutation testing in JavaScript, kind of the available tools, how it works. I will try to give a small live demo, fingers crossed. And ultimately, I want to share some experiences on how mutation testing worked for us at Sentry when I tried it out in the Sentry JavaScript SDK repository. Cool. So let's get started. And I think we all are somewhat competent software developers here, and therefore we would like to know how good the tests we're writing are actually, right? Do they catch things we would introduce? Are they worth the trouble? So how can we do that? I think most of you are familiar with code coverage in one way or another, right? Maybe some of you have some nice fancy badges on their repository readmes or somewhere else. Hopefully it's very green. And for those who maybe are not that much familiar, basically code coverage tells you which parts of your system under test of your code are executed during a test run. And this can come in kind of various flavors. It could be something like line or statement coverage. It could be something like branch coverage, where it shows you kind of which paths through your code were taken. It could be function or class coverage. But the idea is always the same. Basically, it tells you which parts were executed. And that is kind of problematic. And this example obviously is like very superficial. But in a lot of cases, we write tests that are not really testing anything or are very maybe lenient with the things they test. So code coverage doesn't care about that. It will still tell you your code is 100% covered. But, well, if you have something like expect true to be true, that won't really mean anything because you wouldn't catch any bug. And therefore, 100% coverage is nice. It tells you covered everything. But that's essentially where things end. So if you want to kind of play devil's advocate, then you could say the only thing you know for sure is that the parts that are not covered, there you will definitely not find any bugs. But that's more or less it. And that's essentially where mutation testing comes in. And the idea now is that with mutation testing, how does it work? You can basically introduce some pre-generated bug-like code modifications to your system and check if your test suite would actually catch those bugs. So yes, let's maybe do this with a very simple example. Let's say this is my system under test. Massive piece of code, obviously, but it will serve the purpose here. So this is our original piece of code, and now we would like to generate a mutant. And in mutation terms, that is mutation testing terms, that's basically a changed version of your original source code. And you can change this with using so-called mutant operators. They're kind of predefined strategies on how you can modify code. And for example, you can use the equality mutant operator to just invert the equality condition, right? Simple as that. From equals to not equals. You could use something like the conditional operator to replace the previously dynamic condition with just a hard-coded true or false value. Or you could use something like the block statement operator to completely get rid of the contents of your block. This could be a function level, it could be an if block, for whatever, right? And now, in this example here, we have 3 different kinds of mutants. And we will now run our test suite against each of these mutants. And we check for each run, was at least one test failing or did it crash? And then we say that this mutant was killed. And yes, that's the actual terminology. And if that is not the case, if all tests still pass, the test or the mutant has survived, which is probably not great. And we basically rinse and repeat this with all our generated mutants. And ultimately, we will end up with the result, which is the number of all created mutants divided by the number of all killed mutants. So you will end up also with a score between 0 and 1, or essentially a percentage. And the higher the score, the better, because the assumption is that the more of these introduced modifications your test suite actually catches, the more bugs they are able to detect. That's essentially the theory around it. So since this is ViennaJS, let's take a look at how this all works in JavaScript. When I started my research about mutation testing, I quickly found that there is only more or less one tool available that people seem to be excited about, which is called Stryker. I'm just going to briefly go to the website here. This is the tool. It's an open source testing framework. It basically works with almost all popular testing frameworks like Jest, vtest, and so on. It also works for C# and Scala. But it's basically what I showed you, a mutation testing framework that does these 4 basic steps, but it also does a lot of optimizations on top of them. Cool. So it's live demo time. All right. So for this meetup, I basically decided to give you a small demo to kind of demonstrate how mutation testing can help us to improve our tests. And it's not super fancy, it's not a big function or anything, but let's say we are working for a conference and we would like to create a function that determines the price the people pay to get a ticket. And oh, I'm sorry, this is very small. Yeah. Does that work better? Yes. Yeah, that should work better. Okay. Right, so we have a simple function. We would like to basically determine the price of conference tickets, and we have some conventional criteria for conferences to determine this. So for example, we have an early bird reduction factor, basically. We have reductions for students, and also maybe for companies that sponsor the event. If any employee buys the tickets here, they might also get a small deduction. Simple as that, but it has a couple of nice branches in there. It will serve as well. So obviously, calculating a ticket price is kind of risky, right? Because we want to get as much money as possible. So we should test this properly. And like any great software engineer, I told Cursor to write me some tests. And and I ended up with these, and I just had to correct half of them, but I guess it's hit and miss. So we have some super basic tests. We will basically test like the base fee, right? It's 500 for a 30-year-old person who is not an early bird and not a student, works for some company. We will test the student condition. We will test the early bird condition. We will test the company condition. So all nice tests. And let's maybe just run our test suite, check how it does. Oops. So I'm running vtest here, and our output tells us all tests pass. We have 100% coverage in basically all different criteria here. So should be pretty safe, right? What could go wrong? But maybe just to be sure, let's also run a mutation test. And for this, maybe just briefly, I'll show you what it basically takes to install Stryker. It's fairly easy. You basically add these 2 packages, the Stryker core package, which contains the entire mutation testing logic, basically their runtime, and the runner for the test framework you're using. So in my case, that's vtest. It could also be Jest, but they also have like for Karma, for Mocha, for these frameworks as well runners. And yeah, that's it. You then have a small Stryker config file to basically set some options. You can set your package manager. You can define reporters. That's very similar to how you would basically set up coverage. You can say I want to have an HTML report, some progress bar indicator in my terminal. You can specify the runner you're using and some other configuration options. And ultimately, we now just basically have to run this. So let's see how we're doing. So it's now going to start. And we can see it's running some tests. I will just make this a little bit larger. All right, let's maybe look at this from the top. That's badly formatted, sorry about this. We have basically, we see here it found one source file to kind of apply mutations on, which is our ticket price JS file. It found, yeah, it's really good in this thing. It basically found 20 mutations to apply. It's not super visible. Anyway, the important part is basically here. Here we can actually see it. We have a small summary. We have 75% mutation score. So it means of all the mutations we have, which were all in all 20, 15 were killed and 5 survived. So apparently there is some room for improvement. And now we can also fire up the report, which will give us some better answers as to what's going on and where the problems lie. So if I take a look at the file here, I can basically see my function again, and I will see some red lines here. So something is wrong with our early bird condition. And here we already get a clue. It tells me to do change to actual numbers once we know the early bird reduction factor or discount rate. So something isn't really known, and I think that really translates well to what we often deal with, right? We have unclear requirements, we have some things that we just need to figure out, but we still want to incrementally like do some things at least. So maybe we had to make some compromises with testing. And if we now check, so for example here, our mutation test replaced the isEarlyBird flag with a hard-coded false. And when it did this, basically nothing happened, all tests still passed. So that's not great. Basically didn't tell me if I did anything in here that there would have been a problem. And same for what I showed earlier also, kind of removing the condition or like removing the block also basically did nothing. And we can also basically take a look at this one here. Also kind of a common pitfall, right? If we don't pay close attention to testing the borders basically of where the conditions change with, for example, number values, then something might also slip through. So in this case here, changing the operators basically also didn't make the tests fail. And also here, well, if I took Sentry out of the sponsor list, I would have probably paid the full price for this conference, but the tests wouldn't have recognized it. So that's not great. And now we can go back to our actual test suite. Oops. I just fucked up my complete view.
Can I just ask one question?
Sure.
Entirely sure. So Stryker substituted your code with something that you thought of wouldn't make sense to test.
Yes, exactly.
That's very nice.
Yeah, and it does this basically by going through a list of predefined strategies that it knows are likely to kind of relate to actual bugs. Yes?
It runs the whole test suite for every mutation.
Yes, in theory, but it's a bit smarter than this. So what Stryker can do, and I have a couple of slides on this later on, is basically it can determine a per test case coverage, meaning it will be able to tell you which of your tests covers which parts of your code. So in larger systems, this is really helpful because then it will just run a subset of these tests on a specific mutant where it knows like these tests have the potential to actually check for it. So that really speeds up things. Cool, so if I get this thing running again.
You should be able to pull it down.
There we go. Yeah, so I have here a test for the early bird, and maybe this one is a good example here. Maybe this is something we are familiar with in one way or another. We said earlier we don't really know yet what the early bird discount might be. So whoever wrote this test thought, okay, as long as that's the case, let's just check that kind of applying the early bird discount with the student discounts together will result in less than the full amount, so less than 500 here. And that's not really ideal, obviously. We shouldn't write tests like this, but in a lot of cases where it's not as obvious as here, this just happens. And we can now maybe make this a little bit stronger. Let's say this should be the actual value here, and let's just go back and check. So I have 500 as the base price. Early bird currently is set to 0.8, so that makes it 400. And if it's a student below the age of 25, we take half of that, so it's 200. And now I basically can say, okay, for now, as long as I assume it's 0.8, let's just go with 200. And let's run this again. It takes a little bit of a while. And now, well, things already look better. We're at 90% mutation score. So it means something now is not passing anymore. And if we, again, take a look at the report, refresh, there we go, it's 90%. And now the entire early bird block basically is covered by mutation tests, so it won't fail anymore, it won't pass anymore. And we could do the same now for the boundary check and for the sponsor check, but I think you get the idea. And that's generally kind of the idea of mutation testing. You can get a baseline, you go in, take a look at what's actually failing, determine is it worth fixing, do you think that's really a bug that could emerge, and then you can basically take that and adjust your tests as necessary. So that sounds great, right? Give it all a try. Thanks for the talk. Thanks for listening. But unfortunately, it's not that simple. And in reality, we are, as always in software engineering, hit with a couple of problems, with a couple of limitations around it that make this thing a little bit hard to use in practice. And maybe that's also a reason why it's not that common yet. So one of them is the equivalent mutant problem. Again, I have a super simple example here. Here it's maybe very obvious. But if you take a look at the original code, it's a stupid function that adds a plus b. And you take a look at a generated mutant. The only thing it basically changed, it returned b plus a. The behavior of the function wouldn't have changed at all, right? It's completely identical by math laws. And you will basically never get this mutant to be killed as long as your tests actually pass on your original code, which hopefully they do. So this can exist in various forms, and it's basically, it will taint your mutation score, it will just not be killed, and it's also kind of hard to figure out in reality, is this mutant that was created, is it really equivalent? Is there another reason why it's still passing? And yeah, it's just something to be aware of. You can mitigate this with writing equivalent mutant safe code, so kind of rewriting this in a way that it can't be changed by mutations, or maybe it just excludes some of these strategies for code modifications. But ultimately, this can always be a problem. And the second thing, we already touched on this briefly, is of course performance. Imagine you have a test suite with more than 1,000 tests, and you have a system on the chest that's large enough that, let's say, 2,000, 3,000 mutants were generated. Obviously, running all these tests on all these mutants is a massive runtime impact. And I can share some numbers on that later on. But yeah, you could say mutation testing doesn't really scale well with increasing tests, with increasing complexity. And that's somewhat true, although there are some strategies to basically speed it up again. What I talked about before, the selection of specific tests, that's also a really nice way to speed it up. And you can also, for example, run multiple mutations, or you can kind of apply multiple mutations in one code file and only basically switch them at runtime when you're running the tests, and then just rerun the tests more often, which will, for example, reduce the startup time of tests and stuff like this. So there are definitely some things that are basically done to improve this. But yeah, the general problem won't really go away that easily. Yes?
Would you run them each and every time? I mean, figure you would do this once in a while, adapt your tests, and then...
Exactly. I would go as far as saying that's probably the only way how you can run these. And for example, there are some people at Google who basically do mutation testing on their massive monorepo, and they publish some papers about this every now and then. And they also, as far as I know, they kind of run it weekly or something. And yeah, that's, I guess, kind of the way how you would do that in larger projects. Yes.
Is there a ratio between lines of code and possible mutations?
Yeah, the more lines of code you have, the
Yeah,
more
yeah, of
potential mutations you can do.
Factor, whatever.
Oh, that's a good question. I think it really depends ultimately on like the set of mutations you would like to perform, like the operators you can use. I don't really have any numbers on that, but I guess it could be
So
quite
let's
large.
say for a project with 100,000 lines of code,
I can't give you a
test
definitive.
which takes a quarter of an hour.
I think a quarter of an hour is a pretty good runtime actually in mutation testing. Yes.
If a mutation actually just accidentally made your code better,
Mhm.
does it able to recognize it or not?
I mean, you can basically just inspect every mutant, and well, if you find one that makes it better. But yeah, I think one of the most important things is that mutation testing works relatively well as long as your tests are comparatively fast. So if you have short-running unit tests that don't really require a lot of setup, you're pretty much in, let's say, acceptable performance territory. If you have long-running tests, things will take a little bit of a different runtime curve. And yeah, that's kind of the theory behind it. There are some other smaller limitations, but I think those are the most important ones. And now, last part, I will just talk a little bit about how all of this worked when I started to use mutation testing at the Sentry JavaScript SDK code base. I did this during the last hack week at Sentry, which is kind of a week where we are encouraged to work on passion projects, try out new ideas, and just do whatever you basically want. And yeah, I figured let's try this on a real code base. And yeah, so some information about our repository. We have a lot of different tests. We have a couple of thousand unit tests. They are written in Jest and VTest. Basically, our SDKs are downloaded like 10 million times per week or so. So we really try to test stuff well, because otherwise our GitHub is going to flood. We have a lot of integration and end-to-end tests. Those are mostly run with Playwright and also with Jest and a couple of custom stuff around it. And there's already the first gotcha, which is that Stryker, while it supports a lot of frameworks, it unfortunately doesn't support Playwright. So that already kind of eliminated some of our tests to actually be part of the mutation test run. Adding to this, we work in a monorepo. So the Sentry React SDK that you might install with npm will actually depend on other packages, for example, the browser SDK. And this in turn depends on a core SDK, which actually contains most of our logic. But yeah, we kind of have this multi-package architecture and hierarchy. And therefore, we also have tests that basically cover individual packages, but also we have tests that cover an entire hierarchy of packages. And basically, setting this up in a multi-package hierarchy requires some kind of integration test for us. That means, well, we're at Playwright again. And even if we weren't, this would mean that these tests are running super long. They're not running, then basically they can't be mapped back to source code, but to compiled code. So there's a couple of things basically that make our lives a little bit harder. So for this experiment, I basically at some point just said, okay, let's do this only on a package level, which means mostly just unit tests. And to my surprise, this worked fairly well. So random example, the Sentry core package I basically mentioned before has around 1,800 unit tests. And mutation testing initially, when it started, took around 55 minutes. Better than I thought, but obviously not ideal for everyday use, right? And yeah, the duration, I said it's acceptable. But what really surprised me, or what really showed kind of how you can also improve this, is basically by making your individual tests faster. So for example, I switched from chest to vtest, and that already sped it up by 3x basically. So I was basically at 20 minutes. That's amazing. Vtest is really great.
Where do you run it?
These numbers are from CI. If I run it locally, it's a little bit faster, but yeah.
So you added it to the CI then, not just the nightly pipeline, but really to the continuous.
Yes, in this experiment I added it, but it never made it into production. Yeah. We unfortunately can't switch to vtest in reality because Node 14 is the problem. We still support Node 14. Yeah. And vtest only runs officially with Node 18 upwards, but it somewhat works on Node 16 still. But yeah, Node 14 won't cut it. So we're stuck kind of with chest. But also, another thing that's kind of a nice side effect of mutation testing is that I identified like that longer running unit tests, which we also had a couple of, also like really basically prolonged the mutation testing time. So if I then kind of took the initiative and rewrote them, made them much faster, and then also that again reduced the runtime basically of the mutation test runs. So to sum this up from our experiments, mutation testing in our case unfortunately didn't tell the whole story, right? So we got mutation scores. Also maybe on that for the core package, those were 67% initially, which not great, but also not terrible, because ultimately a lot of the things that we basically test are not covered by unit tests, but actually by integration tests, because for Sentry SDKs, it's actually simpler to test in many cases with integration tests. So this really doesn't feed into the whole mutation scores that we got out of these runs. So yeah, 67% doesn't mean that the other tests would have really, or like the other mutations would have really basically not been caught by any tests, which is a bit unfortunate. I wish I could have like told a super great success story here today, but that's unfortunately the reality. And yeah, as we already said, it's too slow to run this on every PR. So we said if we ever basically get this stable and good enough to run in production, it will probably be something that runs once a week, once a day maybe, and we can kind of track the progression over time, which would also be great if there were good tools available to do this. And sure, you can do like a Grafana or some other metrics platform, basically make a dashboard and track it there. Sure, that works. But if you compare this to tools like CodeCuff, for example, that are basically designed to give you information about code coverage progression, that have features like enforcing coverage on a PR or stuff like this, this kind of, let's say, nice developer experience doesn't really exist for mutation testing today. The Stryker folks are actually working on a dashboard solution themselves. I also tried this out, but it's really not more at the moment than the HTML report I showed you earlier with some more statistics, but that's essentially it right now. So maybe this will actually improve in the future. And yeah, let's maybe recap this a little bit. I still think mutation testing is a super cool technique. It's really nice and helpful, and also lets you basically identify some parts in your code that you actually might want to test better. JavaScript also is a great fit, because a lot of these optimization techniques, the per test coverage, stuff like this, is fairly simple to determine in JavaScript, while for other languages, things are a little bit harder there. And as far as I know, this is kind of an unsolved problem, for example, for Java. But yeah, JavaScript just works fairly well for this. And as we kind of also found out, complex code bases with like complex tests are just simply challenging. But I would still encourage everybody to give it a try, check it out. Stryker is open source. Maybe I will add that Playwright runner to get Playwright tests working at some point. But yeah, if you have any questions, feel free to ask. Yes?
Probably yes, but I still have to ask, how does Stryker work with TypeScript?
By default, it will essentially take the TypeScript configuration that you have. You can make it looser, so basically you can create mutations that when you would run TypeScript would actually be caught by the type checker already. So you can kind of make it more lenient, or you can make it a little bit more stricter with overriding specific tsconfig options. So if we maybe go back to the code example here I had before. With like this array here, for example, you could, like, this is a string array now, but you could maybe type it with, specific values or so. If that mutation then actually went in and did this, TypeScript would actually catch it, and the mutant would already be instantly killed. So you can configure Stryker to just say whatever TypeScript catches will also contribute to the mutation score to the killed mutants. Yes?
Have you tried this with front-end code as well?
Not yet. This would definitely be interesting. I think you can use it. Like, I guess if you use React testing library or any of these, it should work basically. Sometimes Stryker requires a little bit more configuration. If you have, for example, a custom chest startup or something like this, then you basically need to do some more stuff on top. But there's always kind of a way to do it.
Do you know of a tool for mutation testing for other programming languages?
Yeah, there exist a couple of. I know, for example, of Pit for Java. That's what I used when I was still in university. I think there is also one for native languages, but I have forgotten the name. I would just maybe Google for mutation testing plus the language. Most frameworks have, most languages have some kind of tool. David?
If I remember correctly, you said that you ended up utilizing this on 1,500 unit tests.
Correct.
How many tests did you end up adjusting then, like for performance reasons or because of the mutants being killed?
I basically adjusted, I have the PR somewhere, I can look it up afterwards. I adjusted, I think, one test suite, like I guess 10 tests or so for speed, which basically increased the overall runtime. And for correctness, or like for improving the mutation score, I started also in the core package. I added a couple of assertions in a couple of tests, nothing too major. It was just 1 week, but I could definitely see some like overall small improvements of the score after making these adjustments.
Cool. So you had solid unit tests already in place, basically.
67%.
But the performance boost is a nice side effect.
Absolutely, yeah. It's definitely a side effect. Yeah. Yes.
Do you think there are any ways, because I mean you described that like for some things it's kind of a pain in the ass, right? And I would also assume that in your example, right, you have the pricing logic and that's the part that you want to test, but you might not care so much about, I don't know, some logic that renders how the button should look like, right, which color or something. It might not be that important.
Yeah.
Is there anything that you can somehow configure this in a sensible way, right? Because if I didn't always have a number that is like 12%, right, it's not usable for me to look at the number and get anything out of it.
Yep. There is definitely some option here. I actually use this in some of our packages. I think it's the mutate option actually. I think this takes this kind of takes basically some glob of files, so you can kind of define which of your source files should actually fall into being mutated. And you can also adjust the different mutation operators. So if you say you don't care about empty block statements or anything because that's too abstract maybe for your use case, then you just disable these and you end up with a smaller number of mutations.
So you also benefit if you already have a good code base.
Yeah, that's it.
Good code.
Yeah.
How does JavaScript work under the hood? How are the mutants generated? Do they do it manually, or is there some tooling that they use? And is this all in memory or file system? And how are the mutants work?
So I can actually show you the mutants. So Stryker will basically, you can configure it to not delete its temp files, which is nice to figure out how all of this works. And obviously, like, this is auto-generated code, so it looks ugly. But let's see. So here, maybe one indicator here that's kind of easy to spot. You have this active mutant flag, which is what I was talking earlier about. Basically, the way how Stryker is able to shove multiple mutants into one file and then switch which one of these is active during runtime. So that basically improves performance. It does this with this active mutant flag. And then here, I think, let's see. Yeah, there's our function. And there basically we see like this, if this mutant is active, then here is an empty block. Otherwise, basically do this. And that's kind of how it stitches all these mutations together. And then on the other side, I don't really have a link to this yet, but I kind of took a look at the source code. You can see kind of how it basically switches through the mutants and then kind of how it catches the test results and calculates the score.
Thank you.
All right, great. Did anyone actually have experience with mutation testing before? How did it work? Did it work out for you?
The bigger the project, the longer the runtime indeed, but
Yeah.
the results are terrifying of what I've missed, although I thought I did TDD.
Yeah.
It makes you humble.
I agree. Now that you say it, I do actually remember we had like one condition that we didn't test in a unit test at all in our core package, which basically canceled the entire SDK setup procedure, and there was just no test for that. So maybe would have been good to add some tests there.